The second example is going to be question number 4, which says an object is launched horizontally with a speed of 8 meters per second from a point 20 meters from the ground. So again, this is going to be a cliff problem, and let's set it up by drawing our picture. So we have 20 meters from the ground. That's how high our cliff is. And we have some object which is launched horizontally at 8 meters per second. So we're going to set up our x and y motion. Again, we're going to separate things in the x, separate things in the y, and list what we know. So we know our initial velocity in the x is going to be 8. We know our displacement in the y is going to be 20. It's actually going to be negative 20. We're going to classify the up direction as positive and the to the right as positive as well. So that's positive y, that's positive x. So because the object is going to start here, it's going to take a path that's going to look like this, right? It's going to hit the ground right here. It's actually moving 20 meters downwards, so that's in the negative direction. What else do we know? We know our initial velocity in the y is 0 because it's launched horizontally. We know our acceleration in the y is gravity, which is, again, just negative 10 or negative 9.81. And the one thing that I can take back and forth is going to be my time. Now, this question has a few different parts, and so the time is going to be dependent upon which actual part of this question we're looking at. So first it says, how long will it take for the object to land on the ground? And the only other thing we might have is s and the x, which we don't know that. So really the first thing it's asking for is the time in the air. So let's do that. So find time in the air. To do that, I'm going to use my motion in the y. That's where I have the most information. So I'm going to set up this equation here based on the information that I'm given. I know, again, my initial velocity is 0, and I'm just going to solve for t here. So I'm going to multiply each side by 2. That's going to give me 2sy equals at squared, because that 2 cancels out with that 1/2. I'm then going to divide by a on each side. It's going to cancel out the a there, and I'm going to write it as this. And t equals 2sy over a y and square root. Because it's t squared, we need to just find t. So I'm going to square root that. 2 negative 20 divided by negative 10. So my negatives go away. Negatives go away, which is nice. We need to square root that. So this is going to be 2 times 20 is 40 divided by 10, which is 4. So the square root of 4, which is going to be 2. So 2 seconds. That's how long I'm in the air for. 2 seconds. Next part. What is the speed of the object 1 second after the launch? So if we think about this, let's not draw that. It's actually not a good representation. This would be, time equals 0 here, time equals 1 there, and then time equals 2 there. All right, so what we have to think about is I like this question. What is the speed of the object 1 second after the launch? So let's actually draw that down here and think about this. So speed 1 second after launch. And so obviously that's going to be just half the way through its motion. But I like what it does. So if we kind of zoom in on our situation, so here's our cliff, here's our object falling down, and again, here's time equals 0, here's time equals 1. We knew up here that it was traveling this direction with a velocity of 8 meters per second in the x. Now, when the object's here, that still is there, 8 meters per second in the x. we're now going to be traveling also with some y velocity as well. So if we just simply understand gravity and acceleration, we could get this number really quick. If we don't remember that, then, in terms of the y motion, what do I know? Okay, so I know my initial velocity in the y is 0. I know my acceleration is -10. I know my time is going to be 1 second, and I'm trying to find my final velocity in the y, right? That's what I'm looking for. So I think the equation that I think would be best is simply velocity equals initial plus acceleration times time. Doing that, this again is 0, and we simply have velocity equals acceleration times time. This is -10 times 1, so the velocity in the y direction is -10. So this arrow here is -10, right? So my ball, 1 second in the air, is traveling horizontally at 8, vertically at -10. So what is the actual speed of it? And so to do that, we have to add these two vectors. So I'm going to add the vectors head to tail and get my total. So this is v total. And in doing so, we would simply just do a little Pythagorean theorem. V total is going to equal v of x squared plus v of y squared and v total squared. Sorry. So the total velocity squared is going to equal x velocity and y velocity. So these are like my two components, and this is my total. Now, when I do that, this obviously becomes, I don't like that yellow, I apologize, but it's going to become the square root of velocity in the x squared plus velocity in the y squared. That's v total. Plugging my numbers in, v total equals 8 squared plus 10 squared. You could throw the negative in, but negative squared is obviously just a positive. So that becomes the square root of 164. And so the velocity total is going to be 12.8 meters per second. So that's actually how fast it would be going 1 second in. So even though it started at 8, 1 second into its motion, it's now traveling at 12.8 because it's increased its vertical component by 10 meters per second. Okay. The next part of the question says, at what angle does the velocity make with the horizontal 1 second after its launch? So looking at this same setup, what we're trying to find now is this theta here. Right, so that's my theta. So 3, or C, I guess in this case, is find theta. So with that, because we have a right triangle here, I can just use tangent, sine, or cosine. I usually like to use tangent just to be consistent with it. So I can say that the tangent of theta equals TOA, so opposite, which is 10 over adjacent, which is 8. I'm going to divide each side by tangent. Divide each side by tangent. I get rid of tangent on this side, and I'm left with theta equals the inverse of tangent of 10 divided by 8. And I'm going to get an angle of 51.3 degrees below the horizontal. So obviously before it was launched horizontally, now we're traveling 51 degrees below the horizontal and at a speed of 12.8 meters per second. Okay. Last part of this one. I like this one. It does a good job of just basic cliff problem, but also looking at vectors and how we manipulate vectors. So with what velocity does the object hit the ground? And so again, when we're looking at velocity, we have to have two things: how fast and which way. So we're almost doing part B and C again, but now for when it hits the ground. So let's go ahead and do that. So 3, or yeah, this is D or 4, I guess. So find velocity at impact. Draw our picture again. We have time equals 0. Impact, we know that's time equals 2, and time equals 1 is there. 8, 8, 8. That doesn't change. Don't say that the velocity right here is 0, right? Yes, once it hits the ground and stops, it's 0, but we're talking about at impact when it's traveling. The other thing that we know is it was 10 here, negative 10. If we know and understand acceleration, we know really quickly that this is going to be negative 20. If we need to do it, it's the same process that we did right here. Same way that we found the velocity at 1 second, it's going to be the same thing using this equation here to find the velocity at 2 seconds. That's how long I'm in the air for, okay? Find the velocity at the impact. Again, what am I going to do? I'm going to add my vectors together. I like the purple better, a little bit easier to see. Velocity total. So we get Vt equals Vx squared plus Vy squared, square root. Vt equals 8 squared plus, now this is 20 squared, square root. Velocity total, once you do all that, it's going to be 21.5 meters per second. Perfect. And again, we need an angle. We need theta here, right? We need a vector, or a vector velocity needs an angle as well. So we're going to do tangent of theta now is equal to 20 over 8. We're going to divide by tangent on each side. And that's going to give us inverse tangent of 20 divided by 8. And we'll get a theta of now 68.2 or 1 degrees. So the actual answer for this would be 21.5 meters per second at 68.2 degrees below the horizontal. And that's how I would find the velocity, both magnitude and direction, when it is hitting. And we'll see the thing that we can understand with this, and this is why we draw projectile motion, going off a cliff like this, is that, okay, my angle here was 53.1, now it's 68.2. It's going to get steeper and steeper and steeper and steeper the longer that it's in the air, because my horizontal velocity doesn't change, but my vertical motion gets bigger and bigger and bigger.